Like you said, my focus and expertise is around reliability and particularly predictive maintenance and or predictive analytics on rotating equipment in industry. And so I'm going to kind of just give you a background of ATEC, who we are, a project that we rolled out across multiple plants, and then go through some very rich use cases or real data and real analytics around rotating equipment. So who ATEC is? ATEC is a company that is a manufacturer, aluminum foundry that makes all the Harley-Davidson cylinder heads. We have a rotomold plastics company that has a couple plants. We do a lot of the large Yeti coolers, but also plastic parts for Caterpillar, for John Deere, etc. And we have a third branch of our business, electronics ruggedization company that does crypto ignition keys and military-based secure memory. And so within that group, that we also do some things within remote tank monitoring, and we've leveraged some of that into our IoT asset offering. So here's just a look at our sites again. Typical manufacturing sites, all focused in the Midwest. Our clients again range from aluminum to plastic to electronics type of clientele. And so we'll move into corporate projects and goals. So the corporate, so my role from a reliability perspective is across our fleet of plants, and the focus of continuous improvement, the focus on reducing operating and maintenance costs, of course, quality improvement and value add services around doing additional machining and additional work on our products to deliver a finished product for our clients. The project goals that we moved into were really focused on reducing unplanned downtime, and the thought there is to use predictive or condition-based maintenance, and then really to increase this visibility and accountability for our plant managers to take care of our assets. Our plants are aging; they're different ages, but the care we're running into some asset failures, and I'll just highlight some of those. So within the past 24 months, we had a number of failures. I think that these kind of caught us by surprise. They weren't debilitating failures, but at the same time, they had an impact on our plants, a risk on some of our personnel, etc. And so of particular interest, this was a makeup air fan. It's up on the roof of one of our aluminum foundry. We had a hard failure. It cost us over $30,000 to repair. We had a second failure on that same fan that was a $10,000 fix. We had a plant air compressor. We had backup air there, but the maintenance cost itself of running to failure was a $20,000 event that we wanted to figure out if we can avoid. And then we had some exhaust fan failures. Primarily the root cause, we believe, was lubrication, and combined they were $12,000 hard costs, not to mention the soft costs around all of these failures. And so if we just started bringing some pictures in, this is 300 horsepower air compressor, screw air compressor that we're speaking to. This is the east makeup air fan on our roof, and here's what an exhaust fan in our environment looks like. So as we went into this, of course, in hindsight, you can come back and look at things differently, but we looked at the failure modes of our equipment, the root cause, and really they were lubrication related. There was a bearing fault, there was a misalignment fault, and there was some imbalance faults because of our focus on fans. The fans and compressors are the scenarios in our situation, and as I'll get to, we've got an artificial intelligence model that addresses our top failure modes. So when we look at industry, how does our failures compare to what industry sees for failures? And so the failures for industry are large in lubrication as a root cause as well. Some folks in industry will argue it's 40 to 80%. When I talk to some customers, they'll argue that I'm wrong, Craig. Maybe it's closer to 90%. And then bearing, roller element bearing failures and then imbalance are the tops. And the asset types can vary. Again, I'm focused on rotating assets, pumps, fans, compressors, gearboxes, and the others. We have robots, we have conveyors, we have anything that's motor driven would be essentially an element of it is rotating. And then the industries that this data came from were across the board, from manufacturing to ethanol to paper to power to chemical, mining, you name it. So just to kind of fast forward to our results, and then we'll fill in the gaps as the presentation goes. As I mentioned earlier, we had an east makeup air fan failure. We put our monitoring in on our systems, and we were able to identify a problem on our west makeup air. We'll give you more detail, but this is the wear in the shaft that we found on that fan. And so we were able to tie out, in this case, because we had a previous failure and what the catastrophic damage was, we had hard costs that we could be very firm on our avoided cost of failure of this fan. Additionally, we had mentioned a 200 horsepower compressor that had a failure. This is our 300 horsepower compressor. They're redundant. And here is the defect on the bearing. And if let run to failure, would have resulted in similar hard costs, maybe a little bit more on a bigger motor. And so we're able to tie that out. And then on our exhaust fan failures, this is a close-up of that fan bearing. We were able to identify lubrication problems, provide the right amount of lubrication at the right times to avoid the failures that we're seeing here. So we're getting at $66,000 in hard savings across an $18,000 investment and a payback of less than 4 months. So let's fill in the gap. Let's fill in the details of the project and the technology. And so as we looked at the project, of course, we had many things we wanted to accomplish. What I wanted to really highlight is that it was very clear that our alerts couldn't just be an alert. They needed to provide a very clear, concise, descriptive action. And then two is we wanted to be able to monitor this from afar ourselves, as well as bring in external help very easily. So when we looked at deploying, if you looked at a typical plant environment with the infrastructure, you've got your sensors coming into an I/O system, you got your operations or OT environment, and then integrating to an IT environment, and then moving up into a cloud environment, perhaps. With our assets being on the roof or in a utility room spread around our plant, we didn't want to invest in an infrastructure just yet. So we deployed cellular technology and beamed it from the sensor directly to the cloud. And we really preserved it as a separate system to establish our security, so we didn't have ties back into our operations. And so by being separate, we were very secure from that perspective. And then we wanted to be in the cloud to be able to have this visibility, to be able to text out, email out, and leverage existing infrastructure of cellular, and then ultimately infrastructure of your cell phone. We wanted to drive the alerts or emails right to the folks' smartphones that was already there. So the investment was in sensors only, and then leveraging infrastructure, existing infrastructure. So really the thought then is, what are the enabling technologies that we could use? So again, cellular, text messaging, email, internet browser. We don't have software in this environment. Cloud data we used. The phone and the camera we used to make visual reminders of where our sensors are at, how they're mounted, what the asset is. Across our different assets, we can use Google Maps to locate where they're at and drill down as we look to scale. We can use the voice recognition to launch the program. We don't use an app on the phone. We just use a login on a website, so there's no software and no apps to load or maintain. And then we're doing some of our artificial intelligence and calculations up in AWS Lambda, which is a place where we can execute code in the cloud and just pay per execution of the code. So no, again, no infrastructure on our half. It's very scalable by being in the cloud. So then what we wanted to really look at is the market. What does this mean? This 18,000 sensors, running in the cloud and on cellular comes at a cost. So on a 3-year support agreement, there is a cost there. You can look at it a couple different ways, cost per asset, et cetera. But just changing the mentality of traditional infrastructure. We don't have a separate piece of software for text email. We don't have a separate piece of software for smart alerts or a separate I/O system. It's all, the way we're doing that's all included in that environment. It is not limited by users. It's really, you pay for the sensor and then you have this connection and then you go from there, which is really a different way of looking at it. There's pros and cons there, of course, as well, but very different look at how we put this together. So next, to move into the technology, if we kind of organize the thought of the technology through the 7 layers of Internet of Things, from your things to connectivity to the infrastructure and on up, that'll be my format of how I deliver our thoughts and deployment. And so just another way to organize it, the source would be a sensor, vibration / ultrasonic sensor that we magnetically connect to the bearings of the asset. In the alert fashion, being able to drive alerts that are, in our case, we're a 24/5 operation. We have normal outages on the weekend, and so if you have a alert condition, we didn't want to alert on Monday mornings when things started up, so we wanted some smartness there. We also deployed a artificial intelligence model or a rule model. In our case, we arrived at RPM as our feature set, so when we did our work, it was a hybrid model of machine and human learning. And we could set alerts not based on statistics or past or machine learning. We could, because that data was not available to us in the time we wanted it, we wanted to see if we could deploy alerts for our assets right out of the gate. And then we have an AI model or an artificial intelligence model to take an alert and break out the alerts by their different severity and create a very descriptive or prescriptive exactly what you need to do as a maintenance guy when you get this alert. And then ultimately deliver that into the people or process via, in our case, the CMMS system, so we could automate that work order. So nobody's really watching this. They can get an alert on their phone, but what's more interesting is to get that alert into an automated work order so that they can use their existing processes and existing people to execute the work. So we'll go through each one of these sections in some more detail. So for the source, we were interested in getting the right sensor in the right location with the right sample rate with the right edge computing. And so if you looked at our biggest hitter, lubrication, if you looked at the vibration and ultrasonic data, you'll see that this green is the failure and blue is what good looks like. And so most of the energy in a lubrication fault is above 4,000 hertz. Many of the vibration sensors available today in this space are 0 to 1,000 hertz. And so they're great at late stage failures of imbalance or misalignment, but vibration of itself, 0 to 1,000 hertz, does not give you that predictive or early warning. That's in the ultrasonic space. So we were clear to make sure that our sensor measured what we wanted to remedy. On the connection piece, Wi-Fi or cellular, we again chose cellular because we wanted to leverage existing infrastructure and our assets were spread out. We wanted device management capability, and so in here we can trend our connection attempts, we can trend the temperature of the electronics, we can trend the signal strength, and so we can not only troubleshoot at any given time, but also know how that looked over a period of time. That was important to us. In the edge, if we're using a sensor that can do ultrasonic, it's sampling at 100,000 samples a second. To push that data over cellular would not be practical. And so we process that on the edge. We wake up, we take 10 seconds of data is the way that was found to be most useful. So we take 1 million readings per wake up per sensor. We are typically doing a 1-hour wake up on these devices. That's what you'll see on our trends. And so we're taking 24 million readings per day. That's a lot of data. And so our approach to handling big data over our environment is to crunch that down, reduce it into calculations of the 0 to 1,000 hertz overall vibe, which is good for late stage problems of misalignment, imbalance, looseness. But what's different and important is that 0 to 25,000 hertz to get at these peak faults around lubrication or bearings. And those we can get early warning 30, 60, 90 days in advance, which allows us to plan and schedule that maintenance. The next piece is powering technology. We went with a battery that will allow us to do 1-hour update rates. We could line power it, and we could go down to wake these up if we have something we want to troubleshoot. We can do as fast as a 15-minute update rate, but it consumes your battery faster. So we wanted that flexibility. On the connection side, so again, just working through these 7 elements of IoT as we look at it, connecting it and making that work. If we didn't have cellular for whatever reason, we wanted the ability for the device to store, and when it made a reconnection, to forward that data and rebuild it. So we're time stamping our data in the edge. So here's what the data begins to look like. This is our 300 horsepower screw compressor, and we're gonna look at that detail of information here in a little bit. Further on the enabling technologies, if you move to your desktop or laptop and you want to organize or understand what's going on with your assets, tabular view with the standard filter, sort, drill down, we wanted to manage. But we also wanted to include metadata or additional data about that asset. So what RPM is it running, perhaps what lubrication type, and also CMMS ID, our maintenance management ID, so we can tie out what we're seeing with our sensor all the way to that CMMS system to generate that work order. On the store and alert, on the alert side of it, we wanted to get the right alerts. We were sensitized to getting too many alerts, because then when a real one comes in, you don't believe it. And so we do a couple things. One is this function ignores the alarm clear, so we can tell if the machine turns off for a normal deal on the weekend. It goes to a low vibration. And so we ignore clearing that, which essentially holds that alert on. So even if that asset had a problem and we turn it off, we still want to remember there's a problem. And so we remember there's a problem, and we don't re-alert when it restarts. 2, as we looked at IoT systems, not all of them really had this hysteresis function. This has the ability to create a deadband around that alert. So it'll trip at this, but it has to clear well below that before we establish a re-alert. So essentially it has to be fixed before we re-alert. And then just a belt and suspenders is, here's a scenario based on time. Hey, if there's something wonky going on here and I just don't want to hear from that but once a day. If we're truly being predictive about this and we're seeing things 30, 60, 90 days in advance, I don't need to be alarmed on it every minute it happens or every hour. I want to have some reprieve from that. So here's our scenario around our rules or our model around setting alert limits. What was troublesome when you would set a baseline is if you had an asset that already had a problem, you didn't have a viable alert. And so you started out your IoT journey missing something, and that was a problem for us. So again, we're targeted at lubrication and bearing faults, and imbalance is on our next model. But this is just looking at our high frequency in Gs, or units of acceleration. And if the asset, depending on the RPM, is the only factor that we use to set the alert, and our assets all ran between 600 and 6,000 RPM, so we could use 6, 12, and 18 Gs universal alerts across our assets. And then for the vibration, which is naturally a later stage problem, but we use the ISO standard, ISO 10816. Again, it's driven a little bit by, it's driven by RPM, and our alerts there were 0.2, 0.5, and 1 inch per second. And this is good, again, for misalignment and imbalance. So again, using a baseline to set the alerts and detect an anomaly would produce some nuisance alerts for us, we felt. And there was no context of the severity. So as soon as I get an alert, the questions from our plant were, now what? What do I do? What's severity? How fast do I need to respond? And so by using a model, we were able to address that. So again, back to this scenario, when we do our analyze, this case, when we started monitoring it, we had a pre-existing condition. We didn't know that. But we were able to see alerts here are set at 6, 12, and 18 Gs on our acceleration, and they're set at 0.2 and 0.5 inches per second on our vibration. The green line is our ultrasonic, or our high frequency. The alerts are over here. It's very high in alert. And we had a secondary problem of a misalignment showing up on our overall vibration. Again, above the alert generated by our AI. So we could, so we didn't re-alert on our restarts here. We had that set, and they were able to, I guess we identified this in May, and we had time. Again, and the mentality of this plant and our plants in general is it's still running. It's not shaking that bad. We got a lot of worse shaking machines in this plant than this guy. How do you know? And we said, one, our AI alert model is based on hundreds of thousands of assets and data points. How do you know it's not good? And we had a fortunate position that they had a catastrophic failure on their 200 horsepower air compressor, and we had the discussion, are you willing to take that risk? So over a period of a month or longer, in watching it and moving the monitor to other bearings where they were normal and low, this was an outlier, they began to think maybe there's something to this. And so in along here, they shut that asset off because we had a backup 200 horsepower compressor, and they checked the alignment with a laser. It was off alignment. They went to align it, and it was bolt bound by the motor bolt. And so they said, okay, you're right on that one. That motor had been in and running for many years. I think the plant is 17 years old. It probably was original. And they said we probably could afford to send this motor in now because we had a motor fail on us that cost us quite a bit of money. And so when they took that motor out and that bearing, there was the defect in the bearing of the motor. And so this green line, here's what good looks like. So this is a 4th of July outage. They took out and did this work. They could plan and they can schedule it. When they started up, alignment was still an issue. So we went back and we told the contractor what he needed to do. He didn't do it. We had the data to do the acceptance test. We called him back on his tab and timely to correct that alignment. And this is what a good alignment looks like. Again, under the threshold here and green under this threshold. So our plants are starting to believe in this a little bit, and we have rolled out to our plastics plants now. This is a case from our plastics plant, and so here's our data coming in there. This is from June of this year. And so how would you set, this is our scenario around machine learning and baselining. If you were to do that with machine learning, you would say perhaps that's your baseline. Perhaps that is your alert. With our artificial intelligence for setting our alerts, we set that at 6 Gs, just like we did on our compressor, okay? And with our AI model for our work order, we can tell them very distinctly on a minor alert, go to the field, inspect, and lubricate. 7 days later, because in a real-world life of plant, they don't just go lubricate when you ask them to lubricate, right? It's not an emergency yet. They get around to it. They have a backlog of maintenance that might be 10 or 14 days. That's very normal, right? And we want to, in the world of predictive maintenance, this is where I live in the predictive maintenance world, but we chuckle at guys doing the vibration or condition monitoring because that's a reactive-based condition maintenance, right? We want to be predictive. We want to be early. We want to go into their normal plan. And so they grease it 7 days later, and this is what that line looks like, okay? So if we overlay the vibration data, the blue vibration data, that does not see the lubrication problems. Provides no meaningful information. So this is the same plant, a different fan. This is on a rotor mold plant. I think this is the exhaust fan. Here's our data. Blue line is vibration. Green is our ultrasonic for lube and bearing. AI generates our 6 Gs alert, so we're in alert again. We see that right out of the gate. This is actually an earlier one. This was in May. We called out a field inspect and lubricate. At this point, we weren't smart enough. We were smart enough, we forgot to perhaps. We did not tell them when or how soon they needed to do this. Okay, we didn't say do this in 10 days. So they got around to it at 18 days later. And here's the change. That's what a good lubricated bearing looks like. And they have moved to, and we watched this, I don't have the data up here, about a month later we start getting alerts again. And we asked these guys, what's your preventative maintenance schedule for lubing this? And they said, well, we don't have one, but it seems like we're getting an alert every 30 days. I think we'll put this on a monthly, right? So here's back to our metals plant. If you remember, our east makeup error is the one that failed. This is the one that we identified early. We had a nice, convenient scenario where they had the sister asset fail catastrophically, significant cost. They put the monitor on here in July 9th. It was 6 Gs. We told them field inspect and lubricate. They went and inspected it, and they saw a gap between the bearing and the shaft. So they were able to plan to create a structure that they could mount a bearing. They wanted to leave this shaft and structure in place, even though there was quite a bit of wear on this shaft. They felt they could create a base back in here and use a split bearing. They never used a split bearing before. They had to field engineer this. This was not supported by the OEM. There was quite a bit of concern. But they had a contractor they had some confidence in. We had a maintenance guy who had some experience using split bearings. And given enough time, they felt comfortable doing a retrofit in the field. And so they built that, put in the split bearing, and here you can see again what that looks like. But it was 60 days of planning and scheduling to pull off a modification like this. So again, it's that ability to see it very early. So we had talked about this artificial intelligence model, or our rules model, for our different alerts. So on the ultrasonic or high frequency, we have 3 levels of alerts. On our vibration, we have 3 levels of alerts. Our big hitters of lubrication, bearing, and imbalance. So this one takes care of lubrication and bearing. And then this minor alert on my vibration, if it's a fan, so I have metadata if it's a fan, then I can strobe it and inspect it for cleanliness. And then I can evolve the actions from there. But this has worked out well for us so far. So in concluding then, we look at this PDM value chain much like a chain. So it's only as strong as its weakest link. So when we looked at this 7 elements of IoT, we felt if we didn't get it right on any one of these, we would miss the end result, which is integrating to our people and telling them what to do. If we didn't have the right sensor for monitoring vibration only or trying to use motor current, we wouldn't be predictive. If we weren't doing the right update rate or have the flexibility on the COM options, we would have struggled to deploy. If we didn't have the ability to connect out to the CMMS with some metadata, we wouldn't get all the way to our people. If we didn't have the right alert tools, we would be sending, could you imagine all these work orders that come out on you? If we didn't have the right artificial intelligence, we'd be missing all of these problems in our assets. And if we didn't have this app with this artificial intelligence to make it very prescriptive, we wouldn't be able to make this connection to our existing people and process. So with that, any questions?